A very good evening to all the members who have joined online today. On behalf of SSI Trivandrum chapter, I welcome you all to this talk 13 of SSI 20 minutes talk series Plenty in 20. Uh, our chairman is held up with the DTR which is going on even now. So we'll commence the talk because we want to keep up the time of 20 minutes. So before we go into the talk series today, let me briefly introduce the speaker of the day, Sri V. Rajasekar. Sri Rajasekar has obtained his B honors in mechanical engineering from AC Tech Karekudi. Subsequently, he has taken MTech in engineering in machine design from College of Engineering, Trivandrum. Not stopping with this, he has proceeded further marketing management from IGNOU. He has joined Vikram Sarabhai Space Center, Tirunelveli in 1990 in the Launch Vehicle Integration Division of PSLV project. Presently, he holds a post of Associate Project Director, Human Rated Launch Vehicle, GSLV Mark III project. He is holding a professional membership in many societies, which includes a life membership of Aeronautical Society of India, Society of Aerospace Manufacturing Engineers, Astronautical Society of India, Amateur Astronomy Association of Kerala, Tamil Nadu Astronomy and Science Society. As an amateur astronomer, science enthusiast, and bibliophile, it's only apt that he's going to deliver the 13th talk of this series. And I think every one of us is eagerly waiting to listen to him. And he'll be delivering a talk on the enigma of black holes. So, with this brief introductions, may I hand over to Sri Rajasekar to deliver the talk. Thank you.
Yes, thank you for the nice introduction, ma'am, and good evening, all. So let me start my sharing. Yes, hope you're getting my screen.
Yes, sir. Yes, sir.
Yeah. Good evening, friends. I think this is the 13th, exactly 1 year back. We commenced the 20 in 20 talk with the inaugural talk by our Westfield director, Dr. Unikishnan Nair. Happy to be here on this platform with all of you. The first 1 minute, 10 seconds I'll take to introduce the topic why I chose this. Whenever you go to any school or college asking for giving an world specific lecture, even though you talk more about rockets, a question will arise on black holes. And every one of us naturally used to enjoy this particular question because children are more oriented towards the mysterious phenomena. So naturally, question will come on black holes. So that's why I chose this particular topic. And before that, I wish to record homage to Professor Jayant Vishnu Nalika, the pioneer of Indian astrophysics. In fact, he used to be known as the Carl Sagan of India. And why I chose this particular slide is he wrote a small book on black holes, okay, published by NBT. That is also there, but maybe this may not be there in our library. But many of his books are available in our library, and they are very, very beautiful texts. Okay, so naturally, I suggest all of you to go through Dr. Narlika's books. Okay, with this, I will just enter into this. I will be providing you 4 or 5 definitions for what is a black hole. So, suppose if it is a KG student, there is even kids they used to ask what is a black hole. So, we need to tell is it's not a hole, it's simply a black color star. You cannot see a black color object in the sky, so naturally you cannot see a black color star. Okay, that is for the KG students. But when it comes to school students, naturally there also you can say it's not a hole, but you can go a little bit deeper. A massive dead star which is invisible because it is black. Naturally, black color star only. Okay, coming to the adults. So high school students and adults, no. So naturally, for them, you can say that it is a dead star, a remnant of a massive dead star, so massive that its escape velocity is greater than the velocity of light. So naturally, we know its velocity is 11.3 kilometers per second. Naturally, for sun it is 617 kilometers per second. So for the black hole, the escape velocity is going to be the greater than velocity of light. So even light cannot escape out of its gravity to show its presence. So that's the definition for adults. But when it comes to the real physicist, literally it will be a lot of jargons are involved here. Infinitely deep gravitational potential well in the space-time fabric, which leads to a singularity as envisioned by Einstein's general theory of relativity, where all the laws of physics break down. So literally what we intend to say is, assuming space-time to be something like a rubber sheet, you put a place of a small ball of iron, something like a shot put ball, if you put it, that it takes a bent shape. So now that is how the space-time fabric is bent near the massive object. So suppose if the mass is it goes on bigger and bigger, naturally it extends and goes to a deep well as seen in the third figure. And this is the black hole. When this particular point, all laws of physics literally vanish. They do not apply to that particular point. See, that is what a black hole is. So this way we can define a black hole. And furthermore, in the modern 21st century, the string theory, where they sell, typically a black hole will be characterized by even horizon called the area beyond which anything which goes in will not come out. That's called the even horizon. Whereas the point where the center core becomes a singularity, I already told you that singularity, where in this string theory, what they tell is something like a fuzzball. Okay, naturally there is no even horizon and no singularity, and what they say is the laws of quantum mechanics may apply there. That is the latest thing in the black hole phenomena. Okay, with a small introduction about black holes, how they can be formed. If you see, I already told it's a remnant of a massive star. So naturally, massive stars, they explode into a supernova, leaving either a neutron star or a black hole. So the core becomes a black hole. Black because it emits or reflects any light, and hole because anything which enters can never escape out of it. And there is another interesting phenomena. What is being proposed is only so far no proof exists for this particular thing. A black hole can form from radiation as well, as opposed to matter condensing into a black hole. Even radiation energy itself can, because E is equal to mc square. So naturally energy also condenses to form a black hole, which is known as a Kujal blitz. Okay, once again it will take decades worth of light of all stars within 350 light years of the earth to make an earth-sized Kujal blitz. Okay, this is very interesting phenomena. And typically, if you see the typical parts of the black hole, there is going to be a core which is a singularity, and with that singularity portion only is shown as the black hole shadow, right? And there is a photon ring. The photon ring is nothing but where the orbital velocity is equal to the velocity of light. It's called a photon ring or a photon sphere, where light is continuously going around and round and round. I'll come to it about later. And naturally, if you can see something going up and coming down, that whatever you see in the top is nothing but back side of the black hole, which is projected to the top. Literally, light is bent, so naturally that also will be visible in the front face of it. That is what physicists tell. Once again, as told earlier, black holes are gravitationally collapsed objects. Gravity is so strong, not even light can escape. And this was predicted by the general relativity theory proposed by Sir Albert Einstein, right? So this is the proton sphere I was telling about it, where the orbital velocity is equal to the velocity of light, whose radius is going to be 1.5 times the. We will come to what is partial radius. And the interesting fact is, if you are on the photon sphere in that particular orbit, you can see the back of your head, because the light from your back side of your head will be coming to your front also. So literally you'll be seeing your back of your head. Okay, that's the interesting phenomena. That is why it's so mysterious. And then once again, black holes are completely characterized by only three parameters. One is the mass of the black hole, the spin, whether what speed, whether right or left spin, and the charge of the black hole. Okay, I'm not a trained physicist to go beyond this. Okay, and once again, black holes with the same mass and charge, they will look exactly the same, and they are literally indistinguishable. Anything with the same mass, spin and charge will look alike. So naturally, you cannot distinguish one from the other. For which it was comically mentioned by one astrophysicist by name J.A. Wheeler, who only gave this name black hole to this particular object. He told black holes have no hair, and it is popularly known as the black hole no hair theorem. Okay, and then just a glimpse of how stars form. So a small star whose mass is less than 1.4 times the solar mass, which is called the Rajasekar limit, will become a white dwarf, and slightly more. Beyond that, either it will become a neutron star or a black hole. That phenomena only we are going to see little bit of history into that. Okay, so 1.4 is our Chandrasekhar limit. Next level is neutron star, and the last thing is going to be the black hole. Okay, I already told you this. So the gravitation, they collapse into that. The gravity is literally balanced by the internal pressure of the star. The moment the end of its period, it will be taken care by the electron degeneracy pressure. That's the term called for it. The electrons, they literally, the protons and neutrons, they still can move around, but everything is in a compact state. And 1 spoon mass of this white dwarf star will be weighing a ton. And if you take neutron star, it will be weighing 1,000 tons. Black hole, literally infinity. And this is the limits what was proposed. 1.4 times the solar mass is the Chandrasekhar limit. More than 3 is going to be the black hole, and between 1.4 and 3. But now this limit has come down to 2.16. Okay, they will be called neutron stars. And this is how a star is going to be born, and finally they will be dying in a very, very ferocious way, literally swallowing so many of the planets surrounding it, and then it goes. And once again, there are four different types of uh, black holes. Okay, stellar mass black holes. Typically, when massive stars explode into a supernova, either a neutron star or a black hole will be formed. They are called stellar mass black holes. And subsequently, the typically hundred to thousands of solar masses black holes, they are called intermediate mass black holes. Literally, they are very, very rare to find, because they are formed only when the stellar mass black holes collide with each other and form into a single object. They are called intermediate mass black holes. And the supermassive black holes, they literally exist in the center of all galaxies. In fact, there is one black hole which resides in the center of our Milky Way galaxy, and it is called the Sagittarius A, because it lies in the constellation of Sagittarius. And there is the fourth class of primordial black holes, which are formed at the time of the Big Bang itself, right? Right at that time. So far, we have not found out any primordial black holes. They may be of the even very, very smallest size also. That is what astrophysicists, they are now discussing. That is the thing about the types of black holes. And coming to the Indian connection of black holes, what is the Indian connection? The first thing dates back to 1756, when the Nawab of Bengal, Siraj Dowlah, he accused 146 British soldiers in a dungeon of 14 by 18 square feet of small room in Fort William. So on that particular, because they all were accused inside and they died there itself, and that was known as the black hole of Calcutta. It was reported long back in one of the newspapers. And what they used to comically say is the post office, the general post office of Calcutta lies in that particular building. That is why Calcutta people, they complained that their letters are not coming out, right? And then comes there is another thing. In between only I'll show 3-4 slides on the Indian connection. Then we'll come to the sequentially. One John Mitchell, he was in England, and he then itself he told there may be classical bodies whose escape velocities may be greater than the speed of light. They are called black stars, though. So you can see my first definition comes from John Mitchell and our famous Laplace, famous for our Laplace transforms, because all of us, we would have studied in our engineering and science degrees about Laplace transformation. And the same Laplace, he wrote one book, The System of Worlds, where he also tells about the dark body whose gravity is so powerful so that light cannot come out. That particular time we had only the wave theory of light. When suddenly, corpuscular theory of light, when wave theory of light also came, he thought, and then he removed that portion of the discussion of dark bodies from his book. Okay, that was history. And then comes our great Sir Albert Einstein. He proposes the general theory of relativity and the field equations of gravity. And once again, this gentleman, he was a weather researcher during the World War I, and there he once again he solves the equations of Einstein, and he tells that there are some singularity regions where gravity is so strong that even light cannot escape. So Einstein told this too bizarre to be true. He didn't, in fact, agree to that. But then came the Indian physicist from Chennai. Okay, he was traveling from Chennai to Cambridge to take a course on master's degree in physics. And during his the voyage in the ship, he solves the equations, and he predicts that lowest mass of a star with which can form a white dwarf. Once again, those days, no, they were all only theories only. So Chandrasekhar literally identifies this theory, and when he goes to Cambridge and he gives his talk, the most famous astrophysicist of that time, Sir Arthur Eddington, he refutes the idea flatly, and Chandrasekhar could not come out, and none of the physicists also supported his theory. And finally, white dwarfs also were thought. Then Chandrasekhar went on to, he continued his the research to give the complete mathematical theory of black holes. This particular book is available in our library, but it's very, very hard to assimilate for us engineers. Probably if you can try your hand. And then he is literally every 10 years, he used to change his subject and make beautiful textbooks. And then that is Chandrasekhar. And literally, Chandrasekhar, had he not been encouraged, he would have solved it in the 1920s itself. Okay, that was Chandrasekhar, the great son of the soil. And then there was one Bisweshwar Dutt called Bishu, and he worked out the mathematical calculation for the whole theory in 1938. However, he couldn't make it. He died before he completed things. Later, Robert Oppenheimer, famous for that atom bomb, and his friend David Snyder, no, they made a calculation and they called this Oppenheimer-Snyder collapse. And they, once again, Vishu is known as the black hole man of India, and he calculated this. This is the paper on massive neutron cores, and he calculated, but literally he shifted his research from astrophysics to atom bomb. So literally astrophysics lost a great scientist. Otherwise, he would have made much more discoveries then. Okay, you probably would have seen this. Oppenheimer changed the way physics works. And then comes the another connection with India. Amal Kumar Ray Chaudhary, and he also obtains a result for a singularity, and it's called the Ray Chaudhary equation, which Hawking and Roger Penrose took, and they solved it, and that's how they became famous. And in between, I told about the Narlikar, no? Narlikar and his friend Fred Hoyle, they are very famous for the quasi-steady state theory of cosmology. That's the other part. And then they never believed Big Bang theory. In fact, Fred Hoyle is the man who gave the Big Bang theory its name. In fact, he ridiculously called that explosion to be, is it has it started with the Big Bang, like that? He asked the same. That's how Big Bang cosmology got its name. And then these two gentlemen, they together asked, how massive should a star be so as to form a galaxy-like structure? And they proposed there should be at the center there should be a very, very supermassive star. And they only first two they asked this question, and then subsequently, I'll coming back to Stephen Hawking. Stephen Hawking and Roger Penrose, they only solved the equation of Ray Chaudhary equation, and they did a lot of research. And then Hawking gave out the Hawking radiation. That means black holes are not really black, and they slowly leak out radiation. Maybe over eons of era, they will be leaking out, and the black holes also will have their natural death, right? So that was that. And then this is Stephen Hawking and Roger Penrose. They built the Ray Chaudhary's equation, and they did a lot of research. And had Hawking been alive, he also would have received the Nobel Prize for the black holes in the year 2020. And it was shared by Roger Penrose and Andrea Ghez and Reinhard Genzel. These two, later two gentlemen, no, the man and the lady, they actually find the supermassive object at the center of our galaxy, and for which they got the Nobel Prize. And in fact, this particular presentation was originally made in the year 2020, and some of the states are even older than that. Okay, and really, do black holes exist in the real universe? Only so far we have seen only the hypothetical cases. Are they really there? Yes, there is one constellation in the sky. Probably night 9 o'clock, you can go and see this constellation. If the sky is cloudy, cloudless, then you can see three stars in forming an isosceles triangle in the northern hemisphere. Northern side, you can see this triangle, and one of the corner stars is called the Deneb. This corner star is the Deneb, and this is the constellation is called also called the Northern Cross. Okay, here there is one star called Cygnus X1. Okay, Cygnus X1 is literally an X-ray source. At the same location, they found out another star called HD 226868. Okay, this particular star is a blue supergiant star. This companion X-ray companion, it is literally drawing material from the supergiant star, and in the process, X-rays are generated by a phenomena called Bremsstrahlung. Okay, it's a German term, and naturally these X-rays only were identified, and that's why it got its designation as Cygnus X1. Okay, X-ray source. But then they observed the period of the wobble of the star. No, it is making in 5.6 days. That means something is going around in 5.6 days. So naturally, Kepler's third law gives you a mass of more than 5 solar masses for the unseen companion, which naturally means it cannot be a neutron star. It should be a black hole only. This particular phenomena. This is it. Once again, it is around 7,200 light years away from. So orbital period is 5.6 days. I already told. Black hole mostly is around 21 suns. Okay. So naturally, this is the sun to the size of this black hole. So naturally, this is the first confirmed black hole. With this, Hawking had a bet with this particular astrophysicist named Kip Thorne. Probably you would have seen the movie Interstellar. He was the scientist behind the movie to visualize the Gargantua black hole shown in that movie. Okay, so naturally they had a bet. Hawking told black holes did not actually exist much. If they did not exist, then actually it will be incorrect. That's what he told. Acknowledge he has lost the bet, and that was a bet between two big astrophysicists. Okay, that's one thing I already told about this Interstellar movie, and this is the M87 galaxy. In the center there is a black hole. They already told. They photographed it using a system of radio telescopes known as the Event Horizon Telescope. Basically, this many as to data have been compiled by a process called interferometry, and with that they released this particular beautiful image of a black hole in the year 2019. Originally, data was started collecting. They started collecting the data from 2017 onwards, but they published it in 2019, and that literally turned the astrophysical world upside down, so that people were astonished at it, and a lot of queries. I already told about this, and then yeah. Can Earth form a black hole? Yes, it is possible, provided if you can squeeze the Earth into the size of a small grapefruit. I already calculated. Nothing is a simple formula only. Your escape velocity, instead of 11.2 kilometer, you can have, you just put c. C means our velocity of light into that. It comes to around 9 mm diameter radius. That means 9 into 20 mm. This much size, if you get, it can be squeezed. But where will you go for that energy to squeeze the Earth into a small grapefruit? And naturally, if it is done, then Earth also will become a black hole. And naturally, what will happen if when a black hole hits Earth? Literally, if it directly comes out, we are gone, right? Or there is a phenomena called spaghettification. So literally, it will be squeezed like it, and tidal forces will shred the planet apart. Whether it is an astronaut or a Earth or any other object, will be literally skews. The tidal forces will shred it totally. Or there is another thing, that is a fire, wall of fire, which will incinerate any object which goes near the black hole. That is it. Otherwise, beyond that particular limit called the event horizon, will not be disturbed. Okay, so that is it for our thing. And one final word I just want to conclude. The black hole teaches us that space can be crumpled like a piece of paper into an infinitesimal dot. That time can be extinguished like a blown out flame, and that the laws of physics that we regard as sacred, as immutable, or anything but nothing. Okay, with that I close the thing. These are all some of the books you want to read, and some of the books are available in our library also. Wish you all the best. Thank you.
Good evening, all. So you have completed maybe. Okay, thank you. Due to paucity of time, we are not able to completely answer all questions in the chat box. May I request the speaker to kindly answer 1 or 2 questions in 5 to 10 minutes from the chat box. Remaining questions shall be answered in person later.
Okay. Can you read, ma'am?
The chat box.
Could not see.
Nothing has come in the chat box. Directly somebody can ask questions.
Yeah.
There's no questions.
Hello.
Shall
Yeah, this is Dhekne here. It was
sir?
it was a wonderful talk by Rajasekar. Very simple terms, he has explained the things about black hole. I just wanted to know what are the new developments in this area. I mean, now this theory has been developed and talked about for decades now. So what are the new things happening in this area? You can
Sir, new things actually, our James Webb Space Telescope is revolutionizing in giving more inputs to the astrophysics. That is point one. But still more theoretical research also goes in parallel, because most of the things about the black holes are theoretical in nature only. So naturally, many theorists are putting many more theories. I already told you, regarding the string theory of the black holes. Literally, black holes are like first balls where you can literally, there is no event horizon or no singularity. That also can be defined. Now they are trying to define it using two theories. One is the loop quantum gravity, and the other one is the string theory, where the one tries to quantize the space-time itself. Loop quantum gravity tries to quantize the space-time fabric itself, whereas here they want to they try to concentrate more on the singularity. So these are the main things now going on in the theoretical astrophysics of black holes.
Right, right.
Parallelly, observational aids also, especially the gravitational wave observatories at LIGO, what is they called? That also is trying to find out more and more black hole mergers, neutron star black hole merger, black hole neutron star merger. All these things are also parallelly being attempted, and that is also throwing a lot of light on the way black holes behave.
Yeah. In fact, you talked about many books being available in our library.
Yes,
long back, I remember reading Lighter Side of Gravity by Professor Narayakar.
Naligar,
That
yes,
is
that's a
there
very
in our
nice book.
library. I think people can go through, our friends can go through even Chandra's biography by Kameshwar Wali. That is another good book. It's a simple book to read anyway about Chandrasekhar. And I remember he had visited VSSC.
Yes, sir. There is one countdown
in
issue where his
84.
interview is published in VSSC. Yeah.
Yes, yes, yes. So after he got his Nobel, he was invited. I mean, when he visited India. Yeah, that's right. So, I mean, our friends can go through many such interesting books, even on string theory. Of course, it is very difficult to grasp all the concepts of that, but that book also is there in our library.
Yeah.
Okay, very good topic you have chosen. And thank you, the organizers also, for choosing this topic. Thank you.
Thank you.
Rajasekar, Jaykumar here. Could join only late. Thank you. Thank you.
Yeah, thank you.
Yeah. So let me end. Any more questions are there? Okay. Let me enter into my responsibility of thanking the speaker of the day. It was indeed a great time we have spent with you, sir. At the outset, let me thank the speaker on behalf of the Executive Committee of SSI. And on behalf of everyone present, I extend my heartfelt thanks to Mr. Rajasekar, who is APD of HLVM3, for his enlightening talk on the enigma of black holes. You have taken us on a fascinating journey into these mysterious cosmic giants, invisible yet immensely powerful, where space and time themselves are wrapped. And many questions remain unanswered despite decades of study. This connects Einstein's theory with quantum physics as unsolved puzzle in science. Your insight has turned a complex subject into an engaging story of science, curiosity, and wonder. This offers clues about the origin and fate of the universe. I also thank all executive members of SSI and the audience for your active participation and keen interest, which made this section truly enriching. Thank you. Thank you once again for the one and all, those who have attended the lecture wholeheartedly. This is Mercy AV signing off.
Okay, thank you all. Thank you, Society, for this opportunity also. Thank you.
Thank you.
Thank you, sir. Thank you all.